Even if the very first scheme we came up with, plain RSA, wasn't quite as secure as we would like, we did see that as a system, RSA lends itself very naturally and easily to the design of digital signature schemes. And we were able to continue through use of a hash function to reach through RSA a signature scheme that had the provable security properties we wanted and yet remained nice and natural. In the discrete log domain, things are not quite that way, and it takes some creativity even to come up with plausible digital signature schemes. Yet there's widespread interest in this. One reason is that for the same level of security, discrete log signatures can be quite a bit shorter than RSA ones. Here we're going to describe one important and interesting scheme, the Schnorr signature scheme. So we're back in the discrete log setting. So we're fixing a cyclic group G with generator little g, and its order is denoted M, all of these being public. In this case, unlike in some prior ones, the order M of the group itself is a prime number. We have a hash function whose range is the integers mod m, meaning it returns exponents for the group. In the Schnorr signature scheme, key generation is, as we usually see and expect for discrete log-based systems, the secret key little x is a random exponent, and the public verification key big X is g to that power. When we want to sign a message M, we have access to the signing key little x and to the hash function. The scheme is randomized, unlike full domain hash. We start by picking an exponent little r at random and then raise g to that power to get big R, which is called the commitment. That is hashed together with the message to get what we call a challenge, and that challenge is a point in ZM given the range of the hash function and hence a possible exponent. Now, inside the signature, we put the commitment, and we now create the second part of the signature as given by this equation. It takes the signing key, multiplies by this challenge, adds in the R chosen here, and all that is done in the exponent space, so modulo the group order M. At verification time, we have the public key big X, we have the message and a candidate signature, which is a pair, and of course access to the public hash function. We reject if this commitment is not a group element. If it is, as we expect, we hash the commitment and message to recover the challenge, and we now have to test that S equals this. But not having the secret key, we do that test by raising everything here in as a power in base G. So we take G to the S and compare it to big R times big X raised to the power C. And if those match, then verification accepts X naught. So here the message space is strings of all length, and a signature is a point whose first component is in the group and the second in integer mod m. So let's verify correctness. That means that we assume a signature on a message has been generated as shown here, and we check that it satisfies this equation. Directly, this check passes because here R is a group element. So the important thing is this. So let's raise G to the power S. We get G to the power R plus Cx because of the way S was chosen in signing. And we can write that also, of course, like this. But then we recognize that G to the little r is big R. G to the signing key is the verification key big X. And we have this equation hold. All right. Now, it turns out this works, and this is the theorem capturing that. So we fix again our cyclic group of prime order M, and we consider the scheme, and we let A be some adversary attacking UF-CMA security, and of course it has some resources, some number of queries to the sign oracle, and some to its hash oracle. Because again, of course, this is in the random oracle model for the hash function. And the proof constructs a discrete log adversary, meaning security here is under the assumption of hardness of the discrete log problem in the group, such that the equation shown holds. So this upper bounds the advantage of A in violating UF-CMA security by this term, which involves the advantage of the adversary B we construct in violating security of the discrete log problem, and then a term which involves the group order and adversary resources over here. The running time of B is a little unusually not that of A plus something, but twice that of A plus something. So looking at these terms, this one would be negligible because the group order is usually large enough and these are small enough that even after the squaring, this fraction is relatively small. Here, there's a factor of Q, and more importantly, the square root. The square root makes things worse from the perspective of tightness of the reduction, in the sense that it makes this quantity a little larger. Of course, with a group of large enough size, it all still works out because we can make this negligible. So we're not going to give a full proof of this, but maybe I can sketch just a little bit of the idea, since it illustrates elements of this scheme that are quite different and also quite pervasive across other things in cryptography. So we're handed this adversary A. We know if it's given the public key that it'll run and make queries to its hash oracle and eventually output a forgery. What our adversary B, who's trying to solve the discrete log problem, does is think of the public key as the target and aim to find the secret signing key, which is the discrete log of the public verification key. And it's going to run our A not once but twice. And furthermore, these two runs are going to be related to each other. The result of this is that it's going to end up with two forgeries, which are also related to each other. Importantly, the commitment in the signature, the R part, is actually the same in both forgeries. The second part need not be the same, and it turns out that the message is the same as well. The second condition is, now remember that there are two runs, and in each of them, all the hash queries made by A are getting responses. One of those hash queries will be R concat M, because that's what's used in the forgery. We require that the responses of the random oracle in the two executions to that same query are different, which will be true with very high probability. Now assume that the forgeries are both valid, so the signatures are correct. That means that the signatures obey the equation of the signing algorithm. So the first signature is R plus XC1 mod M, and the second correspondingly. But the R here is the same in both because the commitment is the same. And of course, the signing key is the same in both, but the C's are different. But here now we have two equations in two unknowns. The unknowns are R and X. So we can solve them. And we don't really care about R, but once we solve for X by this formula, we're done because we've recovered the signing key, which is the discrete log of the verification key. We, meaning here our discrete log adversary. Now, looking more closely at the equation which solves for X, we see that it has an inverse. That inverse is in the group ZM star, so it's modulo M. And it's in order to have that inverse exist that we require two things. First, C1 different from C2, which ensures C1, C minus C2 is non-zero. And second, that the group order was a prime, so that every non-zero point in the range up to M minus 1 has such an inverse. Now, this is a rough description of how the inverter proceeds. We also, however, have to analyze its success probability and see, for example, why those square roots are entering and things like that. And that's a little delicate. There's something called the forking lemma that's used to lower bound the probability that these two executions of A related to each other are successful in the sense that these conditions are met. And we have to apply that to actually conclude the theorem. All right, so EdDSA is a signature scheme in the Schnorr style. It's a version of it over an elliptic curve group. And some of the changes it makes are that the signing key is no longer an exponent directly, but rather a random string of some prescribed length, and you obtain the actual signing key by hashing. Also, whereas Schnorr has randomized signing in EdDSA is made deterministic by a general and known technique of setting the randomness R to a hash of the signing key and message. There are several variants of the scheme, but this scheme is very widely employed and standardized, including in various RFCs in PGP and other places. So this is a good reflection of how Schnorr-style signatures and EdDSA in particular are highly influential and used today. This is an exercise which is effectively asking you to see why certain elements, in particular the R in Schnorr signatures, are needed. If we remove them, we end up with attacks. There are other ways to build signatures in the discrete log domain, and one line evolved from the El-Gamal signature scheme. Right now, the most common embodiments are the digital signature algorithm, which is a government standard, and this is over the group of integers mod of prime. For security, the prime has to be fairly large. However, it is standardized in FIPS, but it's not clear to what extent that's going to continue. There's also an elliptic curve version of that, which is also standardized. More interesting, I think, is the BLS scheme. So towards that, let's back up a bit and try to brainstorm about how we might sign with discrete logs, and in particular, say, the computational Diffie-Hellman problem. So let's fix a cyclic group. As usual, we know its generator and its order. Our hash function this time returns points in the group itself. And the key generation algorithm is the usual one. The signing key is a random exponent, and the verification key is g to that power. The way I sign a message, m, given the signing key little x, is take its hash, that results in a group element, and raise that group element to the power of the secret key, and return that as the signature. Okay, now why is this attractive or interesting? Because just looking at it, I kind of have a good sense that this works in the sense that I would expect this to be secure. Why is that? Because creating these signatures without knowing the secret key is effectively solving the CDH problem. It's solving the CDH problem on inputs big X, which is g to the x, and h of m. Because solving CDH for that big X and big Y of that form is exactly saying compute big Y to the little x. Now, of course, you have to simulate signing queries and all that, but that's all plausible and possible, just like we've seen before. And so I think this should work. And effectively, in some sense, it's right. It does work. And yet it doesn't, because we forgot something. We're not just interested in security. It also must be the case that people have to verify signatures. And there seems to be no way to do that over here. If I tell you that S is y to the power little x, and you have the public key big X, there is no natural way to check that the claim is correct. I could give you something completely different, and you wouldn't be able to tell. So how do we add verification? Well, we're going to use some of the algebra that was developed somewhat more recently for this, which is bilinear maps. So recall what a bilinear map is. We have now two groups, our original one G and something called a target group. both have the same order m. And we have a function which takes two inputs, both in the first group, and returns output in the second group. And the properties it has is that if you have any generator of the first group, if you evaluate the bilinear map on g to the power x and g to the power y, what you get is the result of the map on the generator itself raised to the power the product of the two exponents. Secondly, you have a non-triviality condition, which is that the result of the generator of the bilinear map on the generator twice is a generator of the target group. Now, most often, and indeed for us, the group order will be a prime number. Now notice that from this bilinearity, you also get the following equation. Take any elements of the group, the first group, and exponents. If I want to take the bilinear map on a to the x and b to the y, it's the same as if I shuffle the exponents around. In other words, I can move exponents wherever I want. I can move the y to this side and the x here, but many other things work too. I could put both the x and the y here. I could put no exponents here and put them both outside. Exponents travel quite nicely. The hard problems in this domain include CDH, in particular CDH in our original group G, and the ones we've seen before, and you could think of them in either group. But one thing that's different here is to consider what's called the DDH, or decision Diffie-Hellman problem. This says, like CDH, suppose I have input big X, g to the little x, big Y, g to the little y. Of course, I don't know little x, little y. Now, CDH would say, what is g to the power x, y? Figure it out. DDH says, here is a candidate. Tell me if I got it right or not. In typical groups of the type we've seen before, this problem can also be hard. But that's not the case when you have a pairing or bilinear map, because you can check whether z is the right value through this equation. Evaluate E on x and y. Since exponents travel wherever you want, that will give you E of g to the x, g to the y is e to the gg, E of gg to the xy. And that's the same here. Right? The exponent on g to the xy here just goes out. That is going to help us because we're going to use that fact for verification. Now we go back to our prior idea and we throw in a verification algorithm. But now we're in a setting where we have this bilinear map. We're assuming here the groups are of prime order. They have the same order. And as before, G is a generator of the first group, and our hash function is onto the group itself. Key generation is before, signing is before. How do we verify? Well, first we check that the signature indeed is a point in the first group, otherwise we reject. And if that's true, we recreate the hash over here. Now we need to check that CDH was correctly solved, that S is indeed y raised to the power little x, knowing big X. And the equation comes to this over here. So the message space is all strings and the signature is a group point. And here's the correctness check, which shows us why this equation is there. So we've generated a signature on a message M through signing key little x. So that signature is y to the little x. So let's see what happens when we do a bilinear map on the signature and generator. Well, the signature is y to the x, so we get this. But remember from before, exponents go wherever you want. I can shunt it to the other side. And there I see we have y and the public verification key, which is exactly what's here. So very elegant and magical way to create verification capability and thereby a full-fledged signature scheme. What about security? Well, it works again in the random oracle model, and assuming computational Diffie-Hellman is hard in the first group, you can show that BLS signatures satisfy UF-CMA. And here's the formal theorem statement that details the quantitative aspects. So again, we fix our bilinear map and generator of the first group and we have the scheme on the prior slide. We have an adversary trying to violate UF-CMA security, making some number of sign queries and some number of queries to the random oracle. We construct a CDH adversary B such that this holds over here. So here we have the advantage of B, and we do have a multiplying factor saying this could be somewhat bigger, but not too much. This is very analogous to RSA full domain hash. So if you remember there, we saw two theorems, one with a slightly larger factor here and then one with this factor. And the same path can be followed here, and I've only stated the somewhat better one. But the bottom line takeaway is that BLS is UF-CMA security in the random oracle model, assuming CDH is hard in the first group. So BLS is also a very popular and appreciated signature scheme, and here are some of the reasons. One is that the signatures are short. Compared to Schnorr signatures, they're about half the length for the same level of security. For example, if you want 128-bit security, a BLS signature would be 256 bits, while the Schnorr one and the EdDSA ones would be 512 bits. Another nice property is that BLS signatures permit what's called aggregation. Here you imagine that many signatures have been created on many different messages, possibly even under different public verification keys. But BLS allows you to compact all of those signatures into a single representative aggregate signature, which is as short and has the same size as one BLS signature. So you can achieve quite a bit of space savings through this. Also, there are many extensions of digital signatures, multi-signatures, threshold signatures. Multi-signatures are becoming quite interesting in blockchain and cryptocurrency applications these days. And BLS lends itself quite easily to these kinds of extensions due to nice algebraic properties. We've seen that in our study of signature schemes, sometimes the signing algorithm has been randomized. In that case, we call the signature scheme randomized, but not always. For example, randomized signature schemes included the probabilistic RSA signature schemes and Schnorr, EdDSA, and DSA, but not full domain hash and not BLS. So what's going on there? Randomization is not necessary for digital signatures. You can achieve security without it. Now, that's a contrast to encryption, where without randomness, the type of security you want is not achievable. When you do have randomness, one must beware that a vulnerability is created if you're not careful about how you pick it. In particular, twice using the same coins can lead to secret key extraction in Schnorr. These kinds of difficulties have led people to desire to make the schemes deterministic. And it turns out that there's a canonical way to do that. If you just determine the coins as a hash of the signing key and message, you can make schemes deterministic, effectively de-randomizing them. And that's often done in practice. Finally, we've only touched on the most basic types of signatures. Over the 30-odd years that signatures have existed, cryptographers have created a whole slew of variations and extensions and fascinating protocols which are different types of signatures. And I wouldn't have an exhaustive list, but already here you can see many types of things: aggregate signatures, anonymous, blind, chameleon, convertible, delegatable, forward secure, functional, fuzzy, group signatures, homomorphic, identity-based, invariant, keymorphic, leakage-resilient, link, list signatures, malleable, multi-signatures, online, offline, partially blind, policy-based, proactive, redactable, re-randomizable, ring signatures, sanitizable, structure-preserving, threshold, transitive, undeniable, unique, and like I said, the list isn't complete.